Well, thank you. First of all, thank you all for being here. And thanks to the organizers, not only for inviting me, but also for creating this space, which I think is necessary. I've had a great time at this conference so far. And I hope you all too, and I hope I won't ruin that time in the next hour. So I will talk about cluster algebras. Most of the talk will be about cluster algebras. And that's a bit of an issue for me because cluster algebras are very technical. The definition is extremely technical. So bear with me for the next few slides. I will give the full definition, but then I will try to give you a feeling on what cluster algebras should be. Okay? Okay. So first of all, I will always work over the complex numbers. You can do all of this over the integers, but I won't. And a cluster algebra is a domain over C, an integral domain over C, but it is not given to you by generators and relations. It is given to you by a very different sort of process. So what we do is we start with a field of transcendence degree R over C. So just think of rational functions in R variables. And a cluster algebra is a subring of this field, but it is given to you by specifying a possibly infinite set of generators C, which are known as the cluster variables of the cluster algebra A. This cannot be just any set, otherwise this would be too general. The set C has to satisfy two properties. First of all, C can be written as the union, and I'm just saying union, not disjoint. This is just as the union of finite sets of the same cardinality, which is equal to the transcendence degree of F over C. Okay? Each one of these finite sets, which this is supposed to be like mat BBX, is known as a cluster. So a cluster algebra is something that you form out of clusters. Okay? Well, this is still too general. You can basically partition any set into a disunion of sets of cardinality R. So that second part of the definition is that in order to know who all the cluster variables are, it is enough to know a single cluster. So if you know one cluster, there is a way to obtain all the other clusters via a procedure called mutation. Okay? And that's the heart of the definition of cluster algebra is this mutation procedure. Okay? So you start with a cluster, and this cluster is going to come with a rule to mutate it in order to create other clusters. And you keep creating, you keep mutating and mutating and mutating. At the end, you will get a possibly infinite number of elements of this field F. And the cluster algebra is a subalgebra generated by all these elements. Okay? But the heart, as I was saying, is this mutation process.
When you say that X, amount of the X is a generating set, it's like not each X generates the whole F.
Each X generates the whole F. Thank you. Okay. F is the field of rational functions in the elements of X for any cluster X. Okay. Okay. And I should say everything I will say in this first part is due to Fomin and Selivinsky, who defined cluster algebras around the year 2000. And there is a great book, a great textbook on the archive by Fomin, Williams, and Selivinsky in several chapters throughout the years. Okay. I think they're not done writing it yet. So I want to move on to this mutation procedure. Are there any other questions? Okay. So let's see how you mutate. So you start with a cluster X, okay, which is again set with R elements, which really generates the field F. And you take some number between 1 and R. The mutation is going to replace the variable xk with another variable xk prime. So you kick one out and bring some other a variable in, and this is determined by the fact that xk times the new variable xk prime is a binomial in the other variables. Okay? In other words, xk prime is that binomial over xk. And the mutation just replaces xk by xk prime. So you replace one by one. Okay? Now, it cannot just be any binomial for the theory to actually work. These binomials have to be given by a quiver. So a quiver for me will be, well, a directed graph with the same number of vertices as the number of cluster variables, and I am going to forbid loops like this, and also directed to cycles. I don't want to have these things, okay? And given that quiver, the way you determine which binomial this is, well, this is, you take all the, well, if you mutate at k, you take all the arrows that go into k, okay? And you take x with the subindex, the target of the arrow. You take the product of all of this, plus the product of all arrows that now go out of k. Okay, yeah.
So if you're mutating different variables, can you choose different quivers for every variable?
No, no. It has to be the same quiver that works for all variables. Thank you. Yeah, yeah. Okay, yeah, yeah. The same quiver here has to work for all variables. Okay. So that's what I mean when I say that it cannot just be any collection of binomials. There is some restrictions here. Okay. Okay. So for example, if I take this quiver, double arrows are fine. Okay. The only thing I don't want is loops and directed to cycles. I can have directed cycles of length bigger than 2. That's fine. Okay. So if I start with x1, x2, x3, and I mutate at x1, what I do is, well, I look at how many, well, which arrows go out of 1. I have 2 arrows that go to 2, so that's why I have here an x2 squared. I have 1 arrow coming into 1, and it comes from 3 plus x3 divided by x1. Okay, this is going to be the new cluster variable. Okay, and you can mutate in every possible direction. Here I mutate at 2, and here I mutate at 3. Okay, and if you want to form all the clusters, you have to keep mutating, and this is where the definition gets a bit more complicated, because once you mutate, you also have to update the quiver. Okay, if you mutate once, the quiver that is going to work for this cluster is not the same as this quiver. Okay? So every time we mutate, we have to mutate the mutation rule by a procedure which is known as quiver mutation. Okay? That's a procedure that's done in 3 steps. Well, at the vertex k, sorry. So for each vertex, you need to update the quiver. So it gets technical. So for each pair of arrows, if I mutate at the vertex k, for each pair of arrows that have k in the middle, you insert a new arrow. Okay? So here, for example, if I mutate at the vertex 1, I have 2 pairs of arrows that have 1 in the middle. So I insert these 2 new arrows from 3 to 2. Then I reverse all the arrows that are incident to k. So I reverse these 2 arrows from 1 to 2. Now I have arrows from 2 to 1. And these 2 arrows from 1 to 3, this arrow from 3 to 1. Now I have an arrow from 1 to 2. Okay? And note that this quiver I obtained, it has directed 2 cycles. And I said from the beginning, I don't want to have directed 2 cycles. Okay? So I changed the quiver here, sorry. I delete a maximal collection of directed 2 cycles, okay? So here I change from, I don't know why I didn't do it in the previous slides, from 2 to 3 arrows, okay? So here I insert these new 3 arrows here. And here, well, I have to delete one of these directed 2 cycles, okay? And this is the new quiver. So that's the mutation of the quiver at the vertex 1. Any questions so far? Yeah. Yes, I lost an arrow from 2 to 1. Sorry, there should be an extra arrow here. Yeah. Yeah. It is determined up to isomorphism. So the idea is that, well, here a maximal collection, it could be like these 2 arrows, or these 2 arrows, or these 2 arrows. But other than that, it is determined. That's important when you want to apply cluster algebras to representation theory, but just for the combinatorics, it's not really important. Yes. Mutation is involutive when you mutate at one vertex. So if you mutate at k and then you mutate at k again, you recover the first cluster. Thank you. Yeah. both with the quiver and with the variables. Thanks. It's not obvious. It's also not extremely hard to show. Okay. Yeah. The quiver should be an extra part of the data. Yeah. So the cluster algebra will be determined essentially by a quiver. Okay. Yeah. Any other questions? Okay, so if I keep mutating here, well, then I have this new quiver, and here I would have this new quiver, and so on. And then I need to keep mutating here and keep mutating here, and so on until I form an infinite R regular tree that will have many, many rational functions. Take the union of those, generate an algebra. That is the cluster algebra. Okay. So I was saying, so you start with, well, the piece of data is the variables, which is not really important because you can just take any R algebraically independent variables, and the quiver, and then you mutate once. You keep mutating, and so on until you generate everything. Okay? Okay. So let's do a concrete example. Well, an easy one. Let's take the quiver to be this just one arrow from 1 to 2. Okay. So here, the set of cluster variables, well, let's say that I start with x1 and x2 with this red cluster. And then, well, just to rename, I'm going to replace x1 with x3, x2 with x4, and so on. And here, the mutation of the quiver is only just going to reverse the arrow over and over. Okay. So the mutation here, there is a single rule, which is that xi times xi plus 2 is 1 plus xi plus 1. Yes, but when the quiver is disconnected, you get a product of the cluster algebras for each connected component.
Oh, so you could have chosen the disjoint union of the vertices 1 and 2, and then there's no mutation possible.
There's no mutation, yeah. Yeah. That's just polynomial algebra in x1 and x2. Okay. Yeah, awesome, thank you. Oh, so I start with x1 and x2. I mutate at 1, x1 prime, x2, and I'm just calling this x3. Okay? Yeah, I'm just calling this x3. And I mutate at, well, x2 prime, I call it x4, x3 prime, I call it x5, and so on. Okay? Yeah. So let's see if I really get countable many variables. So if I start mutating, well, I have x1, x2, x3 is 1 plus x2 over x1. Then x4 is 1 plus x3 over x2. And if you do, you know, high score algebra, you find that this is x1 plus x2 plus 1 over x1, x2. You mutate again, and you get this horrible thing. But it simplifies to 1 plus x1 over x2. Mutate again, you get this thing, which simplifies to x1. And then x2 again. So this sequence becomes periodic, and this set that looked very infinite is actually finite. Okay? It just has, I guess, 5 cluster variables. Okay? So in this case, the cluster algebra is just going to be the algebra generated by x1, x2, x3, x4, x5. You can see that you can get x4 from the other variables. So here I just have the algebra generated by x1, x2, x3, x5 with these mutation relations. Okay? That's the cluster algebra. And here I only get finitely many variables. One of the first big theorems of Fomin and Levinsky that to me says that cluster algebras are fundamental is the classification of cluster algebras that have a finite number of cluster variables. And that happens if and only if the quiver you started with is mutation equivalent to an orientation of a Dynkin diagram. So Dynkin diagrams appear everywhere, and they also appear here in cluster algebra theory. Okay? It's not obvious at all, yeah. Well, since I started with quivers, I have to do simply laced. There is a more general definition of a cluster algebra where you start with an anti-symmetrizable matrix, and then you can do other types. Any other questions? Here I have I always forget what the index is. I have two vertices on one row. That's A2 or A3? A2, oh, thank you. But it's associated to SL3, okay, yeah.
I mean, I'm trying to figure out what the significance of 6 periodicity is. Oh, yeah, that's right, 1 to 6. So how could you derive that?
I don't really know about the periodicity. I can tell you about the periodicity of the clusters.
Well, for instance, would it also be periodic? Like, would it be periodic for AN instead of just AN?
It is a bit harder to say what periodic is because you start with like,
Oh, I see.
yeah,
Different paths.
yeah. It will be periodic if you do the right enumeration.
This seems to be a special case because there's only finitely many clusters, right?
Yeah. Absolutely. Yes.
It seems like maybe beyond this case, that's hard to accomplish.
For it to be finitely many clusters, well, in type ADE, there will be finitely many clusters.
Oh, there will?
Yeah, not only finitely many cluster variables. Well, I guess if you have finitely many cluster variables, then you have finitely many clusters. Because there's a finite way of clustering them. Yeah?
Is this variety something recognizable? Like, take away some stuff?
Well, not to me, but maybe to some of you. Yeah.
Generated by x3 and x5, we could ignore x1 and x2.
You can ignore. Yeah. Okay, it is true that this is Grassmannian 2.5 after you insert some frozen variables, but I will define frozen variables later. Okay, yeah. Okay. So let me give you some other example, which is on the opposite end of the spectrum. This was very nice. Now let's consider the so-called Markov cluster algebra. The quiver is this. Okay, so this is like 2 triangle. So you start with cluster with 3 elements, and this is called the Markov cluster algebra because it is very closely related to the Markov equation that Colby talked about on Tuesday. Okay. It's this. It's the same. Yeah. I don't know what the transliteration should be. Mutate the V into double. Yeah. Okay, so you mutate once, you have these new cluster variables. You mutate, well, I'm not gonna mutate in every direction. You mutate here now at x2, you get this. Now if I mutate this at x1, I get this horrible thing. Okay. But then by magic, here on the top, I can factor x2 squared plus x3 squared. And I get this very nice Laurent polynomial. Okay. A priori, there is no reason why this should be a Laurent polynomial. Okay. Now this algebra, in this algebra, the set C is infinite. So you have an infinite number of cluster variables, and in fact, the cluster algebra A is not even Noetherian. Okay. So cluster algebras can be super nice, as the previous one, or they can be super nasty, as this cluster algebra. Okay. And the fact that this is a Laurent polynomial is pretty surprising, and that's another one of the results of Fomin and Levinsky that tell me that this is a very fundamental structure to look at. Before I go there, I want to introduce frozen variables. So it is convenient sometimes to have a cluster and forbid to mutate at some variables. Okay? Those are called frozen variables. You are not allowed to mutate at those. Okay? By convention, I mean, different people have different conventions, but I will make frozen variables invertible in the cluster algebra. That's nicer for geometry. Okay? You get nicer varieties from there. So for example, as an extension of the previous example with this quiver, I can add this new frozen variable, y. I am not allowed to mutate at y. Okay? I will still get 5 cluster variables. And the difference is that where I had a 1, now we have a y. Okay? So you can think of as a family over the cluster algebra with non-frozen variables. Okay. So just keep in mind that in general there will be frozen variables. For most of the applications of the theory, you have frozen variables. Okay, and as I was saying, we have this beautiful theorem of Fomin and Leibniz called the Laurent phenomenon. So you take a cluster algebra, take one cluster, any single cluster, then every element of the cluster algebra can be written as a Laurent polynomial in the elements of that cluster. Okay? A priori, in the mutation rule, you divide and you keep dividing and so on. So you have rational functions. And in fact, you can always cancel things and get a Laurent polynomial. Okay? Now, geometrically, what this is telling us is that if I invert all elements in this cluster, I just get Laurent polynomials. Okay? Because the elements x1 up to xr are already in A. So once I invert, I just get everything here. Okay? So geometrically, this x is going to determine an open embedding of an r-dimensional torus into spec of A. And since A may be non-Noetherian, let me not be very precise about what I mean by spec. Okay? Just imagine the nice case where A is finitely generated and so on. Okay, so I have a torus embedded into spec of A as an open set. This is called a cluster torus. Okay? So every cluster gives me a cluster torus. In spec of the cluster algebra, I have many cluster tori. Okay? So here now we have two definitions. Spec of A I will call the cluster variety. And inside of spec of A I have the union of all the cluster tori. That is called the cluster manifold. Which is a problem in Spanish because we use the same word for variety and manifold. So when I talk to my colleagues in Mexico, I always have to specify what we're talking about because there's been some confusion. And the fact is that the cluster manifold is containing the cluster variety, but in general, this is not an equality. Okay? There may be points which are not in any cluster torus, yes? They are the mutations. Yeah, they are. Yeah, so they are especially nice. Yes.
Manifold is a variety. So what do you mean by naming it this? I mean, it's still an algebraic variety, right?
Okay. The cluster manifold is an algebraic variety. It may not be affine. And the cluster variety may have singularities, which you don't always allow with manifold.
Oh, whereas the manifold will be smooth?
Yeah, the manifold is smooth. As a union of tori it is smooth. Yeah. Okay. But
Spanish should consider.
Yeah, I'll do my best to change that. Yeah. Okay. So in general, this is not an equality. So the cluster manifold is just properly containing the cluster variety, even when the cluster variety is smooth. Okay? As the easiest example, well, we have this cluster algebra. The quiver is very easy. I don't know why. Right? The quiver is just sorry. Since you're not allowed to mutate at y, you only have two clusters. Okay? x1, y and x2, y. And the relation is just that x1, x2 is 1 plus y. Since I am saying that my frozen variables are invertible, this is the same thing as saying that x1, x2 minus 1 is non-zero. okay, because that's the variable one. So in this case, the cluster variety is just C2 minus the hyperbola, x1, x2 minus 1 is equal to 0. Okay? And the clusters, well, one of them is where x1 is non-zero. The other one is when x2 is non-zero, so you're missing the point 0, 0. Okay? So this is the simplest case where the cluster manifold does not equal the cluster variety. Okay. Now, why would you care about cluster algebras? Why, if someone gives you a commutative algebra, why would you care that it has the structure of a cluster algebra? Seems like something very complicated to show even, right? You would need to find the clusters, and you would need to find the mutation rule, and you would need to show that all the clusters generate the algebra. So, well, there are many reasons. First of all, having a cluster structure gives you a notion of what positive points of the variety are. This was one of the original motivations of Fomin and Selevinsky, and this was finally proven in most cases by Schiffer and Lee, and completely generally by Gross, Hacking, Kilcon-Selig. This is related to the third point here. You have a basis of the algebra as a vector space with positive structure constants. Okay? And that basis contains all the cluster variables. You also have relations to mirror symmetry. So you can define a mirror dual of the cluster manifold by gluing tori with a dual gluing rule that I don't want to get in. Okay? You get a very nice combinatorial structure on the cohomology of cluster varieties. You have, well, being a complex variety, you have mixed Hodge structure on the cohomology. This mixed Hodge structure is pure. I don't want to say what that is. And there you can define a curious Lefschetz property that cluster varieties always satisfy. So they give you nice combinatorics. And in general, having a cluster structure gives you a lot of beautiful combinatorics. Okay? But now you will say, okay, I have defined this thing that looks extremely artificial. It has many beautiful properties. But when will I find one of these algebras in the wild? Okay, as Marina was saying, maybe I'm talking about just the empty set. Well, not because I've given you examples, but maybe I'm talking about just some very specific sort of examples. Okay, and after Fomin and Selevinsky defined cluster algebras, people realized that cluster algebras are everywhere, but because they are very technical, they are usually very well hidden. Okay, so if you take a simple algebraic group and its unipotent radical, the algebra of functions on the unipotent radical is a cluster variety. Okay? This was proven in general by Geisler, Leclerc, and Schroer using categorification and preprojective algebra methods. The so-called basic affine space is also a cluster variety. So there is a structure of a cluster algebra here. And many varieties that appear naturally in Lie theory are cluster varieties. The affine cone over the Grassmannian is a cluster variety. This was proven by Scott around 2006, I think. Double Broughat cells, the intersection of a Broughat cell and an opposite Broughat cell is a cluster variety. More generally, double Bott-Samuelson cells, whatever they are cluster varieties. Positron varieties, which are nice varieties appearing in Lie theory combinatorics, are cluster varieties. It was proven recently, well, 2018, I guess, by Galashin and Lam. More generally, Richardson varieties, which you get in the flag variety by intersecting a Schubert cell and an opposite Schubert cell. These are cluster varieties. And all these examples, these 4 examples, they are generalized by so-called braid varieties that I want to define next. These were proven to be cluster varieties in joint work with Roger Casals, Eugene Gorsky, Mikhail Gorsky, they're brothers, Ian Le and Lin Huishen, and separately around the same time by Pavel Galashin, Thomas Lamb, Melissa Sherman Bennett, and David Speyer. And I didn't put here who proved this because the easiest way to prove that Richardson varieties are cluster varieties is to generalize this and then prove it here. From my point of view, there is nothing that distinguishes Richardsons from general braid varieties that I will define next. Are there any questions?
When a cluster variety is Ethereum, it always contains a dense open torus,
Yeah, many.
Yeah, but is it a toric variety?
I think not unless it is a torus already.
Oh.
Yeah. So for a toric variety, you need to extend the action of the torus to the entire variety, right?
So it seems hard to get a characterization of when an abstract variety will be a
And I don't think there is such a characterization. Yeah. And it's pretty hard to show that an abstract variety will be a closure variety.
this is a hard question, but where did this mutation relation come from? Xk, xk prime equals to binomial.
Well, if you ask one of the authors of the original paper, they just say that by experimentation, they found this relation.
Also, a quiver is a quiver a graph that I actually don't know what it is. It has no branches or something.
It is just a directed graph.
Okay, I got a little confused when you said binomial. Because if you have a vertex of degree 3 or greater, and you mutate at that vertex, don't you introduce more variables?
Yeah, but it's still a binomial, right? Because this is a product of just xj to the number of arrows from j to chi. So this is a monomial.
Multiply together everything going in,
Yeah.
and you add to this
Everything going out. Yeah. It's a product. Yeah. So it's a binomial. Yeah.
quiver just means directed graph.
Yeah. Well, and to me, without loops and without directed two cycles. Okay. Now, if you want to show that an abstract variety is a cluster variety, the first thing to do is to find the cluster tori, okay, or candidates for the cluster tori. But then you need to find coordinates on those cluster tori, and you need to find a way to mutate them. So I will tell you, well, I will define braid varieties, and I will tell you how to find some cluster tori, but I won't do all the work. It's way too complicated. Okay, so let me move to braid varieties. To define braid varieties, first I need to define what a braid is. I will just define the positive braid monoid. This is the monoid with generator sigma 1 up to sigma n minus 1. Well, the positive braid monoid with n strands that satisfy these braid relations. So sigma I, sigma j is equal to sigma j, sigma I when I and j are far from each other. And sigma I plus 1, sigma I is equal to sigma I plus 1, sigma I plus 1. I will draw these relations in a second. Okay? So we can imagine this sigma I to be a crossing between two strands. A positive crossing, so the top strand passes over the bottom, the bottom strand. But since I only work with positive braids, I will forget about this orientation of the crossing, and I will just draw it like this, okay? Because I never work with negative crossings. So the relation that sigma I, sigma j is sigma j, sigma I, you can just draw it like this. So apply first sigma j, then sigma I. This is the same thing as first applying sigma I, then sigma j. Okay? And the relation sigma I plus 1, sigma I is just this relation between braids. Okay? And here I did put the overcrossings because, well, it's easier to see if you draw it like this. Okay? So you have, for example, this strand going from the bottom to the top, passing below all the other strands, and so on. Okay. So this is the positive braid monoid. And now for each element in the braid monoid, I will define an algebraic variety that will be the braid variety. Okay? So it's kind of an unfortunate name because people think that its elements are braids, but not really. Just to every braid, we associate a variety that we were not very creative in calling it the braid variety. Okay, so you start with a word in this alphabet, 1 through n minus 1. You draw the corresponding braid, and, well, here's an example. And note that the regions that are determined by this braid come with levels. They are in levels. So if you want to determine the level of a region, for example, this region, just move straight down and count how many strands you pass. Okay? So this is level 4 because here I pass 1, 2, 3, 4 strands. And crossings count as 2 if you want it. Or you can just draw a generic vertical. Okay. Now, to define the braid variety, I will play the following game. For each region here, I will put a subspace of C to the n in such a way that the dimension of the subspace is given by the level of the region. So here I put subspaces of dimension 1 of C to the n, of dimension 2, 3, 4, and so on, okay? And if this reminds you of Jesse's talk from yesterday, it should remind you of that. Okay. This is, well, if I just take the variety given by these configurations, this is too large and it's a product of Grassmannian, so it's not that new. So I will do the following. I will, on the left-hand side regions, I will put the space generated by E1, E1, E2, E1, E2, E3, and so on, where I take the standard canonical basis of Cn. Okay. Then on the right-hand side, I will also put the standard basis, but read in the opposite order. En, En, En minus 1, and so on. Okay. Then I want the crossings to give me inequalities. If I have a crossing at level I want the space Vi to be different from the space Vi prime. Okay. So here, B1 prime is different from B1 double prime, which is different from B1 triple prime, and so on. Okay. It may be that these two are equal, that's fine. But I just don't want consecutive spaces to be the same. And finally, I want neighbor regions to be labeled by spaces that are contained within each other. So if I have Bi on bottom and Bi plus 1 on top, I want Bi to be a subspace of Bi plus 1. Okay? So for example, here, well, I start with this, E1, E1, E2, and so on. With this crossing, I am going to replace this subspace generated by E1 by V1 prime of dimension 1, but I still want it to be contained in this subspace generated by E1 and E2. Okay? So I don't have too much freedom. I have some freedom, but not too much freedom. Okay? And then with this, I will replace E1, E2, E3 with a space B3 prime, but I want it to contain the space generated by E1, E2, and be contained in the space generated by E1, E2, E3, and E4. So I don't have too much freedom each time I create an equation. And the braid variety is just the modulus space of all such configurations. Okay? Any questions?
The simplest possible braid is this. And is this Mr. Grassmannian?
The simplest possible braid? Well, yeah, now this is a great question. Okay, the simplest possible braid is this, right? And here by conditions 1 and 2, well, I have here C2. I have subspaces of C2. Here I need to have E1, and here I need to have E2. So this is just a point.
Oh,
there's nothing to do here.
Oh, the only way to introduce another subspace would be to have an intermediate like that.
Okay, let's do this, okay? So here I have space generated by E1. Here I have a space generated by E2. And here I need to put a one-dimensional space which is not equal to this and not equal to this. Okay? So I have P1 minus 2 points. That's C star. GM, yeah. Okay? Yeah, thank you. This was a great question. All right? And essentially each time you replace, you have like a C word of choices to put the new subspace, okay? And this is going to give you some restrictions on what those coordinates can be. Yeah.
What's the provenance of this? Did someone just start exploring, or was there something that they were trying to model?
Okay, I'm going to say many words that I don't know what they really mean, but this is the space of microlocal rank 1 sheaves. Microlocal is supported on some Legendrian link, which is related to what Jesse said yesterday. Okay. Another motivation is in geometric representation theory. There's something called the Bott-Simonson variety, which is given by sequences of flags. So here I can also interpret this as sequences of flags. I just didn't want to do that. And in the Here I am requiring them to be different. So I have like an open subset of this Bott-Samuelson variety.
This picture doesn't seem to care whether one strand is above another, does it?
No, it doesn't care. No, it doesn't care. To me, all crossings look the same.
Yeah.
Okay.
There's great relations, so would this picture change?
Okay. Let me go there. So yeah, there is braid relations. Okay. And up to canonical isomorphisms, the varieties don't change. Okay. So this is one braid relation, sigma I, sigma j is equal to sigma j, sigma I, when I and j are far from each other. And here, really, the isomorphism is not super complicated, but you just move the crossings, but don't change the spaces. That's not super hard. The other braid relation is a bit harder, but what I claim is that if I know these 4 subspaces, this is forced to be the sum of these 2. Yeah, yeah, exactly. Yeah. Yeah, exactly, yeah, yeah. And then, yeah, exactly, and they're not equal, yeah. Yeah. And here, if I know these 4 subspaces which are the same, this is forced to be the intersection. Okay? So this is why braid relations are preserved, and why this variety doesn't depend on the braid word, but only on the braid defined by it. Okay. And the theorem is that this variety is a cluster variety. In other words, that the algebra of functions, well, this variety is affine, I didn't tell you why, but the algebra of functions is a cluster algebra. And there are 2 constructions of this cluster structure that look very different on the outside, but it was pretty surprising to me to learn that we actually construct the same cluster structure. We have the same cluster variables. Even frozens are the same. They are not even different up to frozens. They are just the same cluster variables. The work of Galashin, Lam, Sherman, Bed, and Spire is based on a beautiful generalization of Plavik graphs, which they call 3D Plavik graphs. That may seem like a contradiction because Plavik means planar bicolored. And then they're saying 3D planar bicolored graphs. The idea here is that they are bicolored graphs which are contained in a surface inside R3. So they're still sort of planar. Okay. Our construction is based on something completely different that we call weaves, and that's what I want to describe next. So weaves are going to give you cluster tori, and well, it's hard then to show that they are cluster tori, but I want to tell you how you get this tori. Are there any questions? Yeah. You get sort of knot invariance. I haven't told you what knot it is, and it's not the knot that you're expecting. So I have a drawing later. Okay? Yeah, but you get some knot invariance.
This braid gives you the A2 cluster, right? Which braid gives you the AN or the other?
Well,
Diagram.
this is A2, but with a frozen. This is just a frozen variable.
A2 with a frozen?
No, it is just a frozen variable. Yeah, just one frozen variable.
That means no mutations at all.
No mutations at all. It's just C star. Now, if you have this, well, I can tell you how to draw the quiver in this case. Okay, and so on. Yeah. This is correct. No, this is not correct. Sorry. Sorry, this is going to give you the. Yeah. So basically, you have. I'm a bit confused here, but yeah, here you only have AN types of quivers, and you keep adding one frozen variable at the end. That's okay. So let me tell you then what weaves are. So I'm going to consider 3 moves on a braid word. 2 of them are just the braid relations, okay? And these give you isomorphisms between braid varieties, canonical ones. The last one is a bit more complicated. It just takes 2 consecutive crossings and collapses this region. Okay? So it takes sigma I to just sigma I. Okay? And this reduces the length of a braid word. And I only want to consider this move oriented from this longer braid word to the smaller braid, to the shorter braid word. Okay? And a weave on a braid beta is just a sequence of rules that takes this braid beta, uses moves A, B, and C, and turns it into a braid where strings meet exactly once. Okay? You can always do that if you start with a complicated enough braid. So for example, here I can apply a braid relation to turn it into this. Then I can collapse this region. Then I can collapse this region. I still have strings meeting more than once, so I apply braid relations and I collapse this region and I end up with this. Okay. So that's a weave. The way weaves relate to braid varieties is that they give you maps between open sets of braid varieties. So we have already seen how to do this, how the braid relations give you isomorphisms between braid varieties. And then the collapsing move, well, you have 3 subspaces, Vi, Vi prime, Vi double prime. Just forget about the middle one. This is not defined on the entire braid variety. It is only defined on the open locus where these 2 spaces are different. Okay? Because I require that crossings give you different subspaces. Okay. And the theorem here is that if you have a weave, you can consider the modulus space of all those assignments where you can do all the weave moves all the way to the end. Okay? That gives you a torus. And the upgrade of this theorem is that this gives you a cluster torus for the cluster structure. Okay? This is a way to obtain not all the cluster tori, because in general you have an infinite number of them, but to obtain many of those cluster tori. So let's look at this example. Sorry if this is a bit too small. Okay? So you start with this. Well, the variety has B1, B2, B1 prime. This is determined. This has to be B1 prime plus the space generated by E2. I do braid moves. I replace this with the intersection of these 2. Okay? And now, when I do this collapsing move, I am requiring that B1 prime is not the subspace generated by E1. That's an open requirement on the braid variety. Okay? I keep going. Now here, I require that space generated by E1 is not the intersection of the space generated by B2 and E2, E3, which is always true. Okay? So when you get like this sort of tautologies, it's a sign that there are frozen variables, which are inverted. Okay? This does not give you anything new. And you can keep going, and well, the next one is going to be that the space generated by E2 is not equal to the space generated by E3, which is also a tautology. So here you have one mutable variable and 2 frozen variables. I'm not telling you how to draw the quiver, but this is how you get at least a feeling for what the cluster variables should be. As I was saying, you get many cluster tori, and in general, many more cluster tori than in more traditional constructions based, for example, on Plavik graphs. But you get only finitely many ones, and in general, you have an infinite number of cluster tori. There is a way to change the definition of a weave to obtain infinitely many cluster tori, but it is not clear to me that you obtain all of them. And in any case, the definition of the locus defined by these more general weaves is very complicated, and I don't think it's easy to work. Okay, so in the next 9 minutes, I guess, I want to give relations between the braid variety and low-dimensional topology. This is what Isaac was asking. Okay? So I'm going to, so I have a positive braid, and I'm going to consider the following link in R3. So this is what I meant when I said that this is not the link you were expecting. So most people just close this on top without crossings. Here, I want to like reverse the strands. And the reason I do that is because remember that I start here with the standard basis read in positive order, and here I read in the reverse order. And this accounts for that. Okay? A conjecture we have with Marco Castronovo, Mikhail Gorsky, and David Speyer is that if this braid closure is a knot, meaning that it has only one connected component, then the cluster variety is equal to the cluster manifold. So every point is containing some cluster torus. Okay? The converse is not true. We can't fix this statement. So if you take this beta, sigma 1, sigma 1, sigma 2, sigma 2, sigma 1, sigma 1, the cluster variety is a torus. So it's just 3 frozen variables completely disjoint from each other. So in this case, the cluster variety is equal to the cluster manifold because they're both just a single torus. But if you look at this braid, you have 2 connected components. Okay? Which I indicated by colors. And for a while we were wondering, well, but it would be super nice to have an if and only if on the previous slide. Okay? What fails here? And the reason that this if and only if statement doesn't hold is because if we look at the purple component, it's given by the strands number 1 and 3 here, which do not cross inside the braid. They cross above, but they don't cross inside the braid. Okay? So that's the problem. That sometimes you might have strands that don't cross inside the braid, but they cross sometimes somewhere above, and then you have something that should be a point in no cluster torus, but the point doesn't really exist, more or less. We can fix the statement of the conjecture to tell you like when we think the cluster variety will be equal to the cluster manifold, but it's much harder to state. So I just leave it like that. More generally, we have the following conjecture that was first like sort of stated in email correspondence between David Speyer and Vivek Shende. Although I think that you said, oh, it would be great if this happened, but that's it. And in some other setting. We have that an element, a sequence of subspaces, belongs to the complement of the union of cluster tori if and only if you can find a decomposition of C to the n, a non-trivial decomposition of C to the n, such that every subspace is given by the direct sum of the intersection of the subspace with the 2 parts of C to the n. So the thing is like disconnected. Okay? Let me probably give you an example. Okay, so here you have E1. Here you have E2. Okay, and according to this conjecture, for a point to not be in any cluster torus, there has to be a decomposition of C2 into 2 subspaces, therefore each one of dimension 1, such that each one of these guys can be written as a direct sum of the intersections of the space with these 2 subspaces. Well, this is forced to be C2 is E1 plus C2. Okay? Because I want these to be given by the intersection of one of them with the other. Okay? So if I want a point which is not in any cluster torus, this is forced to be E2 because it has to be one of these 2. This is forced to be E1. And this is the only point in the cluster which is not in any cluster torus. Okay? If I increase, if I have one more, 1, 3, 4, you can play the same game. Then here you have E2, E1, E2, and you find a contradiction. because these two are supposed to be different. This is telling me that in this case, the cluster variety is equal to the cluster manifold. Okay. So one of the implications is reasonably easy. If you can find the composition of C to the n into two subspaces where this happens, then the corresponding point in the braid variety cannot be in any cluster torus. That's not extremely hard with enough cluster theory behind. The other implication, I think, is much, much harder. And I need your help to prove this. Okay? So let me tell you what our successes have been. Well, we have verified this conjecture for a pretty large number of braids that in particular include braids giving you all finite type cluster algebras. So we can tell you what the complement of the cluster manifold is in all finite type cluster algebras, so ADE type cluster algebras. You could say that maybe you can do this by hand because you have a finite number of cluster tori. So, well, maybe. But we have also verified this in cluster algebras associated to Grassmannian 3n. And these are of infinite type as soon as n is larger than 8. Okay? So you have an infinite number of cluster tori, and we can tell you exactly what is the union of this infinite number of cluster tori. And the way we do this is using these lemma surveys. Somehow those are enough to see the entire cluster manifold. Okay? But of course, Grassmannian 3n, well, it's the easiest infinite type cluster algebra, but there is much, much more to do. And again, I ask for your help here, if any of you has any ideas. And with that, thank you so much for listening.